Okay, so hello. As you heard from Cameron, yesterday we're getting a big new cluster, El Capitan, and this is going to create some adventures for us. Some of this is not related to El Capitan specifically, just the problems that we hear about all the time. Systems are getting bigger, workflows are getting more complicated. But of course, every new system is an opportunity to try and do something better. And in El Capitan's case, one of those new aspects of the system is something called rabbit storage. So what rabbit storage is trying to help with is sort of two-pronged. On the one hand, we have traditional HPC workloads that we're all familiar with. Lots of threads all competing for bandwidth to the global file system. In our case, we often have many simulations running at the same time, either on the same cluster or different clusters. And so they're competing with each other, but the competition is invisible to the users. We've had a few different iterations of local storage or burst buffers that have had pretty mixed success in the sense that they haven't been widely adopted, and apparently they're too hard to use. So what can we do about this? Well, there's always the option of getting the users to change their behavior, but that's too hard. There's making the file system faster just by spending more money and getting faster hardware. But it would be nice if we could spend less money but still get the benefits like Oleg was talking about. So it'd be really cool if we could make burst buffers work better, by which I mean make them easier for applications to integrate. And one way to do that would be, and I'd forgotten about the on-demand cluster file system that I think Andreas mentioned earlier, but something like that. In addition to that, we've got more complex workflows. I think everybody seems to be having these days. And that includes machine learning. It's a really different I/O model, and that our file systems weren't really designed to handle. And also just changes to the way that simulations run generally, where instead of going back and forth between simple compute-only and I/O-only phases, they do more complicated things. So we could, again, try and change the user's behavior. It's off the list. We can attach block storage to compute nodes, which is at least probably easier for some of these codes now than it was when the codes that we were talking about were all sort of built for parallel file systems. But it would be even better if we could attach that local storage in ways so that multiple nodes could access that storage at the same time, and we could use it so that data can be staged in, perhaps before the job runs, but then data that's created on those local file systems can be trickled out to the global file system while the compute is computing and writes are still happening locally as well. So the El Capitan's approach to this is to provide flash storage that's in the compute chassis, but set it up in a way that's more flexible than what we've had in the past. So this compute storage is called Rabbits and consists of two modules. There's a module that has SSDs in it and PCI switches, and the compute nodes in the chassis connect to the SSD via these PCIe switches. But then the Rabbit also has a processing module, has a CPU and a NIC for the high-speed interface, and that processor is also connected to the storage. And so now we've got this storage, and that can be used in a wide variety of ways, right? Maybe it can be connected to only one of the compute nodes if only one of the compute nodes needs it. Or perhaps it can be connected, a little bit of it can be used for all of them, or perhaps it can be used by this processor so that we can get things like direct attached PCIe storage for compute nodes or Lustre targets where the server's running on this compute module or both. But of course, we've got the hardware, but now we have to make it work. We have to integrate it with the system. So we have to control access to the storage so that these nodes don't stomp on each other. We have to set up and tear down file systems or targets, and we have to give the users a way to specify what they need. So at the bottom, we've got our what's for us our usual operating system stack. This is a RHEL-based Linux distribution, but in addition to sort of ordinary Linuxy stuff, it's got ZFS and Lustre. This is what we would. This is the same ZFS and Lustre that we use for our large Lustre file systems, and that allows us to create targets. It's got the kernel drivers so that we can talk to the high-speed interconnect and anything else that's special. And in this case, or rather, because of these rabbits that we're getting, it also includes Flux, which is a resource manager, Kubernetes, and a special software stack specifically for managing the rabbits. So that orchestration stack for managing the rabbits is pretty complex because it needs to do a lot. So it needs to be able to reconfigure the PCIe fabric so that it can control access to that storage. It creates and destroys NVMe namespaces on the SSD to control how much of that storage is visible to the different nodes. And so that allows us to split the SSD storage so that, say, the compute nodes each get a few hundred gigs or a couple terabytes or something, and then the rest of the storage is available for some other use, like a rabbit target or Lustre targets. This rabbit storage also handles things like asynchronous data staging, keep track of the state of the rabbits, and that's all provided in the form of containers, which are then in turn managed by Kubernetes. So wish us luck on the Kubernetes part. This will be new for us. On the compute nodes, there are some daemons. Those are much simpler than the rest of the elements in this picture, and those are just for things like mounting and unmounting the file systems on demand on the compute nodes. So we've got now this rabbit storage, and it's managing the rabbits. We've got the software stacks that's managing the rabbit storage. Now we just need a way to coordinate that at the system level, let the users indicate what they need, and so Flux is providing that role. This is a research manager similar to Slurm or something else. It's newer, and it was created intentionally for scenarios like this, where a system has heterogeneous resources. And in this particular case, the main challenge is that these rabbits are in the compute chassis, and some of these use cases that we're talking about are locality dependent. Other use cases, like the Lustre targets, really aren't, because they're accessed over the network. So Flux lets the user specify what they need. It queries the rabbit orchestration software to find out the state of the various rabbits. It then allocates the specific rabbits, tells the rabbit software to configure the storage appropriately, and then launches the user's jobs. Specifically, the users request what they need by means of data warp directives that are in the job script, and those sort of get translated into a form that Flux can use. And then, as I said, Flux tells the Rabbit orchestration software what to do with each of the individual rabbits. So I just talked about sort of several modes or the flexibility that this Rabbit storage provides, and so that means it essentially provides can provide lots of different interfaces to the user jobs. The one that's most interesting to me, and probably most interesting to people here, the possibility to use it as a Lustre file system. So for us, this will be new. We've had Lustre file systems for as long as there have been Lustre file systems, but they've been central file systems that are typically globally mounted. And now what we'll have are these file systems that are generated on the fly. One or more targets will be created on each Rabbit that a user asks for when they ask for that storage to be in the form of a Lustre file system. And because it's created for the job, not only will it be private to the job and not shared, but it'll also be created in ways that are hopefully tuned well to the job's requirements. So, for example, the user gets to specify how big this file system should be within the bounds of the storage that's available. And they get to specify a profile indicating the kind of workload that their application will produce. And that means we can give them more MDTs and less OSTs, or more OSTs and less MDTs. Because this is all flash, it'll be fast. And because it's in the compute node and they get more Rabbit if they ask for more compute, it scales beautifully. Let's see. It also allows for customization that we're not going to do so in the beginning, of course, this is all new, and we'll all be really, really happy if it just works, right? So step one is just create a Lustre file system that can be mounted on the clients properly. And these Lustre file systems will be more or less configured like the ones that we would otherwise run in our center. But what's most exciting to me about this is that once we get past that hurdle, it allows for quite a bit of other interesting possibilities. So we can do things like enable features that we wouldn't enable in our global file systems. We could use PCC, we could use metadata write-back cache, we could use DNE 2 and 3 from the get-go. When it might not perform well in every use case, but we know it'll perform well in a use case that the user is specifying, or it might be risky just because it's relatively new. In addition to the Lustre use case, as I mentioned, the storage can also be provided or made accessible to the compute nodes directly. In our case, what we'll do is format that with XFS. And just because this isn't complicated enough already, we'll have an option to provide a GFS2 file system, which is a file system that allows multiple nodes that have connections to the same storage, same underlying block storage, to share access to that file system using PCIe for the data transfers and using a network daemon similar to LDLM for locking. In an additional attempt to try and make this to help make these more usable to our users, we're working right now on integrating Rabbit support with scalable checkpoint restart library, which is a library that was created at LLNL to try and make checkpoint restart workloads more efficient. And the goal is both to get that working when the system's available so that applications that already use SCR can easily integrate SCR, get Rabbit usage for free, and also to provide an implementation example. In addition to allowing the users options, just in the, sort of pick what works well for you, because these things are dynamically generated every time a job is kicked off, it means that over time, applications can change the way that they use the rabbits. So we'll see how that goes, but it means potentially applications could start out with usage models that are simpler and more like what they've been doing already, and then graduate to more efficient use cases or more efficient strategies that take some time to implement. So far we've got these machines. We've got some, or rather, I should say, we have prototype machines, early access hardware. We've worked through all kinds of interesting Kubernetes corners and tricks. We found interesting things with about NVMe namespaces and PCI switches, and it's really moving along very well. One of the reasons it's moved along so well is that, a little surprisingly to me, HPE got on board with open sourcing their orchestration stack very early, and have not only open sourced it, but have actually been developing it in the open using GitHub. We also, the Flux resource manager is internal to us, and that team has been developing in the open as well. And one of the consequences of that is that these two teams have been able to work really effectively, getting these two pieces of software integrated. And we've worked through a lot of bugs and a lot of design mistakes in a surprisingly short time because of that. Any questions?
I'm really jealous of your rabbits. Wish it worked for us also. The schedule didn't work, but this is an awesome piece of technology. So, any questions?
Just curious, for your ephemeral Lustre file systems, how are you planning to get the data on and off?
So there's, well, basically DCP. If you're familiar with MPI file utils, that's the mechanism that if the user requests the system stage data in, stage data out, or even transfer data, do asynchronous or rather offloaded transfers while the job is running, that's the underlying tool that'll get used. And we'll see, right? There's all the problems of needing to, of staging in, holding up the delivery of the nodes and that whole mess. And it'll be interesting to see, to me, whether or not this is any better, because of course, if somebody chooses the ephemeral Lustre option, well, the rabbits can be anywhere. They don't need to be in the same chassis as the compute nodes then, because it's accessed over the network anyway. And so I think it raises a possibility that you could potentially allocate the rabbits, start staging the data while you're waiting for the compute nodes. I doubt very much that they'll actually do that, at least initially, because it seems to me it makes the scheduling problem a lot harder. But I think it opens some possibilities.
That's interesting. I was involved in some of the very early stages of this, and that had been discussed. I figured they were going to do it, but it sounds like that's maybe too hard.
Well, I'm just trying to make promises that I'm not the one that has to deliver on them. So I'm really not sure exactly what they're planning to do.
Yeah, so my question was a little bit related. You mentioned for the ephemeral luster versus GFS that the luster option isn't going to use the Rabbit compute partition to do the data stage out.
Oh, no.
And I was wondering-
If I said that, I made a mistake.
In the slide that you
Really?
said.
So it's absolutely true.
One more. So it said go forward one, where it says for the GFS2 node. It's one more forward, maybe. There. So it says when using GFS2, the goal is to do data movement on the Rabbit, but when using Luster, the data movement will be doing the compute nodes, right?
Did I say that somewhere?
Well, it says right on the slide.
Oh, I'm sorry. Okay, I see what you're saying. Yeah, that's a little bit of a misstatement. So data movement really could happen either way, and so SCR or some other checkpoint libraries, many of them have an option to do asynchronous transfers, and they just use pthreads or something like that, right? And so then it's happening on the compute, and that's just the simpler way to do it, I would say. But it's absolutely in the plan to spin up a container on the Rabbit processor when that's possible, given time to make it work.
There was one other question somewhere at the back.
I have a general question on the choice of supporting XFS and GFS2. On what kind of needs do you have for the PCI fabric that you're using it for?
Is the question basically why use GFS2 as opposed to XFS?
Right. In addition to Luster, why do you have a need for XFS and GFS2? For what kind of workloads do you see those kind of use cases?
Okay. So XFS would be something like you've got some application where each node is doing some process that doesn't involve sharing data or where the sharing is infrequent, but it needs basically some scratch storage. So it does some compute, it stores some results, it does something else, then it reads back the results. And an example of that I've seen on our systems are like drug discovery things where they're looking at proteins, and they're often, I don't know that it's necessarily the algorithm, but the codes at least I think are essentially designed to work on one node, and they just need some scratch space. So XFS would be for a use case like that. GFS2, the idea is that if you don't want to, if you have again a workload where an individual node is producing data that needs to end up on the global file system, and it doesn't need to be shared with the other nodes particularly. GFS2 gives you a way that it can be writing that data out to the GFS2 file system, which is local and therefore fast and doesn't have any locking, right? There's no locking involved with the other nodes at least. And then a process running on the Rabbit can be reading that off and bleeding it back to the global file system. And I don't know really what actual applications will use that. It's just to try and give a wide variety of access methods.
I have more questions about your management, because you just sort of touched on it a little bit. Are you using Redfish, Swordfish in the back end to manage the traffic for I/O and stuff? and the Rabbit?
We're using them for monitoring purposes, and I think for things like updating firmware. I'm not
Okay,
sure
you're
what
using
you mean by
Redfish for
using
that?
it for managing traffic.
Okay, because Swordfish sort of handles a lot of the I/O stuff, so you don't know if they're doing that, right?
Okay. I guess I don't know enough about it to know.
Okay.
To my knowledge, we're not using it like that. All right. Oh, wow.
Let's make this the last question.
Hi. So this is more about Kubernetes actually than the Lustre side. But so you're just going to end up with thousands of namespaces, storage classes essentially, as you're spinning up these Lustre file systems in production.
Maybe I don't know enough about Kubernetes to know what a storage class is.
Oh, okay. I guess the other question is, and this is also Kubernetes side, but are you essentially spinning up a namespace per job, or are customers or projects or whatever going to have persistent namespaces in the cluster?
So we plan to support both. There will be, we still have to figure out sort of policy kinds of things, because obviously it's not helpful if somebody camps on all the rabbits and then no one else can use them. But we intend to provide both so that, customers that have, or users that have a sequence of jobs that, create a bunch of data and then process it somehow can do that.
One suggestion, I hope you know, but we have a Lustre Discuss mailing list. Pretty much everybody here should be subscribed to that. I highly recommend, if you have questions about this one, the slides will be uploaded very soon for these presentations. You carry up the discussion on the Lustre Discuss list. That will be a good way of using that mail list for people who are not here as well. Once they have a chance to see the presentation, they can perhaps join into the discussion. That being said, we are ready for the closing remarks, but one quick announcement. Right after the closing remarks, if you like to participate, we'll take a group photo, so come to the podium. If you like to be in a picture, if you don't, that's perfectly fine. But if you want to be in that picture, come to the podium quickly. Let's have a picture. So that's all. Megan.